Welcome to section 2.2, organizing quantitative data and the popular displays. By the end of this lesson, you should be able to organize quantitative data into tables, construct histograms for discrete and continuous data, draw stem and leaf plots, draw dot plots, and identify the shape of a distribution. Okay, in summarizing quantitative data, we first determine whether the data are discrete or continuous. Once we identify whether it is discrete or continuous, like qualitative data, we will organize it into tables. So let's talk about discrete variable first. So discrete variable is a quantitative variable that has either a finite number of possible values or a countable number of values. So since we can list all the possible values, remember quantitative means countable. One way to make a table is just to list all the values along with their corresponding frequency. Here's an example. So what is shown is scored data, or some data that refers to the number of children of some students in their family, including themselves. So an easy way to compile the data is to make a frequency or a relative frequency table, as we did before in the previous section. Another example are the scores in a test. Here are some data from past Math 127 class. Now, sometimes we have too many values to make a row for each one. In that case, we'll need to group several values together. In this case, we'll have to set up intervals of numbers called classes. Each class has a lower class limit and upper class limit, along with the class width. And the class width is the difference between successive lower class limit. It should be the same for each class for consistency. So your lower class limit in this case is 50, your upper class limit is 69, and the class width is 10, because that's the difference between 90 and 80. This 2, and your class width is 10, and it has to be consistent for all the classes. Now, similar to bar graph, we will use histograms to present quantitative data. So a histogram is constructed by drawing rectangles for each class of data. The height of each rectangle is the frequency or relative frequency of the class. The width of each rectangle is the same as, and the rectangles touch each other. Let's have an example. Let's use the data we have in example 1, which is about number of children. So as you can see, we have this data from number 1. So to make a histogram, we make what looks like a bar graph with a couple of key differences. The rectangles must touch, and I can't read that. The class labels are underneath the rectangle. So again, the rectangles need to touch in a histogram because we want to imply that the classes are adjacent. So here's what they'd look like for our example data. You can use Excel, Microsoft Excel, and use the same procedure we had before, but this time you'll choose histogram. If your Excel has the Excel stat add-in. If not, we can use our StatCrunch data, and I will have a separate video on that. Now let's talk about continuous data. Your data are continuous when you can't enter all the possibilities because it's too big or too small or keeps going. In other words, you're just rounding. So if the data are continuous, then the categories of data are, or the classes, must be created using intervals of numbers. So we have to form classes that don't overlap. Again, classes are categories into which data are grouped. Here's an example. For this example, let's consider the average commute for each of the 50 states. This data show the average daily commute of a random sample of 15 states. So as you can see in the table, because our data is continuous, average commute, your classes and class limits did not overlap. You have to have separation. So as you can see here, if you stop at 18 here, the next class should start at 17.9. They should have a separation. By the way, to make frequency or relative frequency for continuous data, we will use the same strategy we'd use for discrete data. And take note that in this case, each rectangle doesn't represent a single value, but rather a range of values. And because of that, we don't label the class on the horizontal axis. Instead, we label the lower class limits, which is, for example, in this case, the lower class limit at the left edge of each rectangle. So for this range, the lower limit is 16, so it's on the left side of the rectangle. For this range, the 18 to 20, the lower limit is 18, so our lower limit should be on the left of this rectangle. Alright, another way to represent quantitative data graphically is the use of stem and leaf plot. So stem and leaf plots gives more detail because they show the actual data. So the idea is to split each data value into two parts, a stem and a leaf. The stem is everything of the rightmost digit, and the leaf is that rightmost digit. So here's an example using the data from earlier regarding exam scores of past Math 127 students. So with this data, the stems are the first digits, 5, 6, 7, 8, and 9. The leaves are all the second digits, so from 0 through 9. The full stem and leaf plot lists the stems down on the left side and a vertical bar between, and then lists the leaves in order to the right. So this plot looks very similar to a histogram, only gives us the actual data. So when you turn this on the other side, it would look like a histogram. However, there are some limitations to stem and leaf plots. In particular, we're limited to small data sets. You don't want to use this if you have 1000 test scores. Also, the range in the data needs to be fairly small. Now here's the last of the popular graphs, the dot plot. Dot plots are similar to single-valued histograms, but rather than placing rectangles above each particular value, a dot plot just places the required number of dots above each value. So looking at our example again in the number of the children, the plot would look something like this. Alright, so and the last thing I want to talk about is looking at different histograms. We have some vocabularies for the distribution shapes. So I have 4 different histograms. The first one you can see is the uniform distribution. The uniform distribution is when frequencies are evenly spread out among values of the variable. The second one is symmetric, or the bell-shaped curve, where the highest value is in the middle and with values tailing off to the right and to the left evenly. The two shapes at the bottom are skewed to one side or the other. The one on the bottom left, this one, if this distribution is about test scores, the test distribution that most people ended up getting is 70s, 80s, 90s, and maybe few people pulling it to the right, to the left, so that this is skewed to the left. And the last one, as you can see, most of the scores are 20, 30, 40, 50, 60. Then there's a few skewing it to the right, so that's skewed to the right. Alright, let's summarize from section 2.2, the quantitative data and popular displays. We talk about discrete data for our tables. The column on the left is just the individual values. If you have continuous data, you have the classes. The key point is that the classes cannot overlap. Alright. We talked about histograms, which their bar graphs have no gap between them because they have to be right next to each other, meaning the values are right next to each other. So if you have 69, so next to 69 is 70. That's the difference between the bar graph and histogram. So we have stem leaf plot also, which is very similar to that. We have the dot plots, and finally we talk about some of the distribution shapes: the uniform, symmetric, skewed left, and skewed right. So that's it for this video. Thanks for watching. Next video is about graphical misrepresentations of data, and I'll see you then.